to the vacation supplement of What Would You Like to Learn Today? I'm Will, and today we're going to be talking a little bit more about the question of how things can be ripped apart by tidal strain. I mentioned this in my last podcast, where I suggested that a lot of the rings of Saturn and the other gas giants may have been caused by tidal forces acting on comets or moons that got a little too close. Today we're going to explore a little bit about why that happens and how that happens. Okay? Now, when we say tides, most of us immediately think of the ocean. High tide, low tide, all that business. I'll get into that later. But when we say tide, what we're really talking about is differences in gravitational attraction between different points on a sphere or on a gravitational body. Okay? When we think about something like a moon or the Earth, it's not really all one thing. Typically in physics questions, we treat them as if they're gravitational point sources, meaning that we're imagining all that mass is concentrated in one point right at the center. And for all intents and purposes, that's true. It explains how things move. We don't need to get too crazy. But when you get two objects close to each other, there end up being different amounts of gravitational force at different points throughout the body. And these differences can end up causing some interesting results. Let's consider, the best way to explain this. Let's imagine we have a moon and a planet, okay? Now, instead of looking at the moon as a whole thing, okay, imagine instead that we just take 4 points, okay, one at the top, one at the bottom, one on each side, okay, that are each on different relationships compared to what it's orbiting around, okay? Now, consider what are going to be the gravitational forces that are acting on those points, all right? And you can actually just consider these as 4 things hanging in space, and they're actually going to be falling because they're falling down towards the gravitational source, okay, in this case, Earth, all right? Now, when they fall, they're all going to fall at different speeds and with different accelerations because they're different distances away from the Earth, okay? The one on top and the one on bottom are going to fall at different speeds. The one on the bottom, meaning the closest to the Earth, is going to be falling the fastest because it's the nearest, okay? Gravity increases the closer you get to something. The one that's further away is going to be falling at a slower speed. The two that are out to the sides are going to have a gravitational attraction somewhere in the middle, but their paths are going to be slightly tilted, okay, because they're offset a little bit, and they're being drawn towards the center of the Earth, which we can still continue to treat as a gravitational point source. Now, look what happens as they fall. You'll notice that although they begin in a classic square formation, as they fall, they kind of elongate out into that diamond, okay? The ones out at the sides end up getting squeezed in, and the ones at the top and bottom end up getting squeezed apart, okay? This makes a little more sense if we do a little bit of quick vector analysis. All right, so these arrows represent the amount of force that each one of these objects is feeling. All right, and what we're going to do is 2 things. First of all, we're going to break them all into horizontal and vertical vectors. Okay, that's easy with the top and bottom ones. The ones out to the sides, since they're at an angle, we end up forming a right triangle. Okay, and if we move those around, we can see that it's got a horizontal vector and a vertical vector. These are called component vectors, and they're useful when you want to break stuff down into their component parts, okay? What we're going to do now is, okay, we're going to subtract out the one vector that they all have in common, okay? And we're going to see what's left when we do that, okay? If these were all part of a moon, the whole moon would be feeling one single gravitational attraction, which happens to be about the same as the vertical component of these side pieces, because they're going to be in the same plane as the center point of the moon, okay? So we're just going to subtract that right away from all of them. What we're left with are small amounts of forces this way and this way at the top and bottom, and some forces at the sides that are squeezing it in. This explains why they formed that formation that we saw earlier. Okay? Now, if we expand this and we look at what is going on over all the points around the surface of a moon, we end up seeing something very much like this. Okay? Now you can see easily that the differences in gravitational attraction. What ends up happening is, as something gets closer and closer, right, as the moon gets closer and closer to whatever it's orbiting around, okay, you end up having these forces getting stronger and stronger. And depending on what the moon is made of, if it's made out of a liquid, for example, that means that these forces have a much greater effect on the shape of the overall body, versus if it's made out of something rigid like rock, then it's going to take a lot more force in order to get any actual change to occur. It gets even more complicated when you consider that a lot of things are kind of solid on the outside and liquid on the inside, the Earth, for example. So it's hard to be really generalized. But what we can say is happening here is the part of the moon that is closest is going to be pulled in, the part that's furthest is going to be pulled away, and the parts of the sides are going to be pulled in. Okay? Now, somebody did the math on this French astronomer named Roche, who figured out that every body has, it's like the danger zone. Okay, if you're a moon and you're orbiting around a large planet, you can't get too close, or else the gravity will increase to the point where these tidal forces are enough to rip it apart. Okay, we saw this, if you remember, back in '94 when shoemaker-levy hit Jupiter. That was actually the second pass that it had made. Okay, shoemaker-levy originally was one comet, then it made a pass, but real close to Jupiter in 1992, where it got ripped apart into a whole chain of little comets. Okay, and then those came back around in 1994, and they slammed into Jupiter. Okay, sequentially. It was actually pretty cool to watch. Although it was a little creepy, since if that had been Earth, that would have destroyed the whole biosphere. Anyway, or at least done some pretty serious damage, dinosaur killer level. Now, if we consider that it depends on what the body is made of. Okay, liquid ones are going to not be able to get that close. There's something called the Roche limit, which basically says that everything, every body, every moon, every comet, whatever, depending on what it's made of and what its density is, and depending on what the density is of whatever it is it's orbiting around, there's only so close that they can get before the tidal strain becomes such that it will be ripped apart. Okay, something with a really high tensile strength, like if you had a diamond moon or something, that's going to be able to get very close before the tidal strain is enough to rip it apart. Okay, something like that, actually, the Roche limit is going to be inside the planet's crust, so you don't really need to worry about it. But if you have something that's liquid or that's made out of something fragile that doesn't really hold well together, then it's going to be further out. The rings of Saturn are all within the Roche limit, meaning that they're not going to be able to clump together and aggregate back into a moon, because the tidal strain is going to pull them apart before that happens. Let's see a little bit about how these rings are forming. So let's say that you're a moon that's getting closer and closer, and eventually you pass through the Roche limit. What's going to end up happening is the forces are first going to kind of pull you out into an ovoid shape, or an elliptical shape, really. And then you're going to start getting broken apart, okay? And then what ends up happening is the chunks are going to start to drift apart, okay? The chunks that happen to be closer to whatever you're orbiting, those are going to appear to move a little bit faster. The chunks that are further out are going to appear to move a little bit slower. They're all moving at the same speed. It's just that they happen to be on different tracks, okay? It's kind of like a NASCAR. The cars all try to drive as close to the center of the ring as they possibly can, because then they have the less total distance in order that they need to actually travel, okay? So they're going the same speed, but because they're going different distances, it's a shorter distance around here than it is out here, okay? So they get pulled apart, and they get streamed out until eventually you have a ring, okay? Now, you can see that here's another little illustration. This is somebody did an analysis. It's an animation of a neutron star getting pulled apart by a black hole, but the same idea is happening. Okay, it's getting close, and then all of a sudden it gets ripped apart. All right. Now, there are some extreme versions of tidal strain that people have thought about, especially in relation to really high density, high gravity things like a black hole. One of the thoughts is, let's say you're getting sucked into a black hole. Okay, in that case, the gravity is going to get so strong that you're going to start to experience tidal strain within your body, okay? And as you get closer and closer, eventually you're going to get pulled into a really long, skinny thing. This is called spaghettification, because it looks like after you're done with it, it looks like a long strand of spaghetti. But that would be an interesting process to undergo, I should say. All right. Well, anyway, that's tidal strain. Later, I think, when I go down to the beach and I try some surfing, we're going to talk a little bit more about tides and how that affects when it's good to go surfing and when it's not. But until then, keep thinking of some good questions, and have a good vacation.